In this video, I wanted to go over an acid-base disorder and how you would approach these blood values down here. So let's go ahead and read through this, what's going on with this patient, and we'll look at the blood values. A forgetful 70-year-old male was diagnosed with heart failure and prescribed a drug called eplerenone, an aldosterone antagonist. The patient forgot he had already taken the drug and overdosed. He started hyperventilating when he realized his mistake and went to the hospital. Below are the results of his blood tests. So let's first look at the pH here of 7.5. 7.5 is a little high considering the normal is 7.35 to 7.45. A high pH is an alkalytic state, so alkalosis. Now we got to figure out why this patient is in alkalosis. We got to see whether it's the respiratory system, which is the CO2, or the bicarbonate. The way we do that is we look at this equation over here. CO2 plus H2O is in equilibrium with an acid plus bicarbonate. So let's first look at the bicarbonate. Normal level for bicarbonate is 24. 15 is a little low. So if we come over here and we look at this equation, so if bicarbonate is low, that would cause this whole system to respond by shifting to the right. That would cause us to have an increased amount of acid in the blood. So this would cause an acidosis, which is not our state. We're in alkalosis, so it's not a metabolic issue. Now let's look at the CO2 levels. A normal value for CO2 is 40. That is also low, but it's on the opposite side of our equation over here. So if CO2 is low, that's going to push this equation over to the left. And that's going to take away our bicarbonate, or it's going to decrease. So that is the cause of our alkalosis. So we know this patient has respiratory alkalosis. That's our primary disorder. So primary disorder is respiratory alkalosis. So respiratory alkalosis. Now we got to check our compensation with the bicarbonate, see if it's compensating properly. The way we do that is there's two different forms of respiratory alkalosis we can have. One is the acute form, and if it's the acute form, bicarbonate HCO3 needs to decrease 2 for every 10 decrease in CO2. If it's the chronic, then bicarbonate needs to decrease by 5 for every 10 decrease in CO2. So let's look at the normal values for CO2 really quick. That's 40. Compare that to what we measured, 25. The difference for that is 15. So we've decreased by 15. So for the acute, if it was an acute, the bicarbonate would have to decrease by 3. So 3 minus 24, that's 21. So we're probably not in an acute state according to these measurements. Now if we look at the chronic here, we'll do the same thing. So if this is going down by 15, well, that's about 7.5. 7.5 minus 24. I just realized these need to be switched. But anyway, you get my drift. That would be about 16.5. That's pretty dang close to what we see up here in this individual. So it looks like the patient might be compensating properly in a chronic form. My guess is that this patient is more has an acute respiratory disorder because of the hyperventilation. But let's go ahead and go through the rest of our blood values to see if we have any secondary disorders that could be affecting our values. So the next thing we check is the anion gap. The anion gap, which normally is 12. Okay? So the way we calculate an anion gap is we take the sodium concentration and we subtract it by the chloride concentration plus the bicarbonate. In this case, it equals 10. That's pretty close to 12, and really 12 and below is a normal anion gap. So this would indicate that it's normal. Anything above 12, and especially if you get up into about the 20 ranges, that means you definitely have a large anion gap metabolic acidosis. That doesn't mean we don't have an acidosis, but that means we don't have a large anion gap acidosis. So we have one more thing to check, which is the excess anion gap. Excess anion gap. The way we do that is we take that 10 that we measured up here and we subtract the normal value for an anion gap, which is 12. That equals -2. And we add that to our measured value for bicarbonate, which was 15 up here. That's our 15 up here. So that is 13. We compare this number 13 to a normal bicarbonate level, which is 24. 13 is less than 24, so we know we have an issue here. If we are lower than 24, that means we have a non-anion gap acidosis. This is our secondary disorder in this patient, a non-anion gap acidosis. If this number was larger, say 30 or 40, then it would be considered a metabolic alkalosis, an underlying metabolic alkalosis. So we have our primary disorder up here, our secondary disorder down here of a non-anion gap acidosis. Now let's look at the patient really quick and see why we have these different blood values. First, I already mentioned this a little bit earlier in the video, is the hyperventilating. If you're hyperventilating, you're decreasing the CO2, which would drive this whole equation over to the left, causing alkalosis. So that is the cause of our primary disorder of respiratory alkalosis. The second disorder of the non-anion gap acidosis has to do with this aldosterone antagonist. With patients with heart failure, oftentimes they have a lot of fluid buildup, so they are given diuretics to let all that fluid, or to get all that fluid off of their chest or their thoracic cavity. So normally this would be a very good thing for this type of a patient. But if you had overdosed, it can go to the extreme. So I'm going to draw a very crude representation of a nephron here. The aldosterone will work over here in the collecting duct. So that's the collecting duct. And it acts to increase the sodium reabsorption, which will cause water to follow it, so H2O, and it causes potassium to be secreted and acid to be secreted. So if we have a lot of aldosterone, we're going to find a lot of acid and potassium in our urine. Now this is an antagonist. So that means all of these arrows need to be switched, or this patient is going to be peeing a lot. They're gonna have a lot of urine, and that's what I was saying by it's going to help with heart failure by getting rid of all that excess water. But if he took too much of it, that means you're also going to have a lot more of this acid in the blood. And that's going to explain our non-anion gap acidosis. Well, I hope you found that helpful to go through a whole problem and to see a primary and a secondary disorder for an acid-base problem. If you have any questions, let me know, and I hope you find this helpful.